Hello, and welcome to this short video series on weighted least squares. Our intent is to provide the viewer with an understanding of weighted least squares technique in order for them to appropriately identify and correctly implement it when conducting regression model diagnostics. Necessary background that is required is the understanding of probability theory, statistical inference, and regression analysis. Throughout the lecture, various concepts will be covered, but emphasis will be placed on solving the problem at hand. The video series will cover the following: introduction and motivation, construction of weighted least squares, a toy model followed by an applied model, and finally diagnostics and conclusion. Recall that the linear regression models are constructed through the method of ordinary least squares. Assessing the aptness of the model for a specific dataset requires an investigation of whether the initial assumptions are met. Our role will focus on what occurs when the assumption of constant variance or homoscedasticity is violated, and resolution of this problem through the weighted least squares technique. Note that the construction of the regression coefficients through ordinary least squares is not dependent on the assumption of constant variance. Observe the homoscedastic residual plot, where our assumption is not violated. Notice how this visually represents the assumption of constant variance, where the residuals are uniformly distributed about the mean zero. If the error terms do not have constant variance, they are said to be heteroscedastic or differing in variance. Compare the two heteroscedastic residual plots against the baseline example, and notice that the residuals are not constant and seem to follow certain trends. Heteroscedasticity can arise as a result of a number of problems, including measurement error, subpopulation differences, interaction effects, or omission of important variables from the model. If these are problems, deal with them first. Don't just jump into other techniques such as weighted least squares because they do not get to the heart of the problem. If there is a violation of the constant variance assumption, this does not result in parameter bias. However, ordinary least squares estimates are no longer the best linear unbiased estimators. That is, among all unbiased estimators, ordinary least squares does not provide the estimate with the smallest variance. Another consequence of heteroscedasticity is biased standard errors. This in turn leads to biased test statistics and biased confidence intervals, resulting in an inefficient regression model. The reason ordinary least squares is not optimal in this case is because it gives equal weight to all observations, when in fact observations with larger disturbance variance contain less information about the position of the true regression line when compared to observations with smaller disturbance variance. Fixing this problem intuitively makes sense. The observations with the smallest error variances should give the best information about the true position of the regression line, and thus the model should be adjusted accordingly. Our motivation for weighted least squares technique is now clear. How do we adjust our regression model so that the variability of the response is constant? In order to solve this problem, we have to correctly specify the variances so that the weighted least squares model is more efficient than the ordinary least squares model. This will be accomplished by taking the original multilinear regression model with heteroscedastic errors and transforming it into a model with homoscedastic errors. To summarize our first video, we recall our objective was to provide an understanding of the weighted least squares technique. So far, we have identified our problem and the consequences that arose from it. This has given us the motivation of deducing a strategy to solve it. The following video will introduce the weighted least squares approach to solving this problem of heteroscedasticity in linear regression models. Thank you.